A spherical oil drop has radius of 1.2 times 10 negative 6. Density is rho. Show the mass of oil drop is this. So we need to show M. Rho mv. Oh, there's one equation we know, that is the density equation. Density equals to mass over volume. If we forgot that already, oh, maybe we want to write down a little bit. So if you want to find mass, mass equals to rho times V volume. At this point, if you got this somewhere in your working, you can put a check mark there and say, oh, I remember density is mass over volume. That's one mark for the equation. Now we need to sub in all the things that we know. Density, 940 kilogram per meter. Volume, they didn't really give volume, they give radius. So I think we'll need to do an assumption here. They said spherical. It's not an assumption, it's a calculation. So it means the oil drop is going to be a sphere. And it will have a radius. So the volume of a sphere is 4 over 3 pi r cubed. So we need to write that here. 4 over 3 pi, I can put r in another bracket, r cube. Okay, and you should get at the end the value that they're trying to prove, which is 6.8 times 10 negative 15. So if you plug in, especially the correct values inside, density and 4 over 3 pi r cubed, that's another one to get your final answer. So this one is a show question. So if you must remember to show, you can show. Let's say you did not get to figure out this one. It's okay. You take this value and you move on to the next part. Part 2. The oil drop is charged. Explain why. It is impossible for the magnitude of the charge to be 8.0 times 10 to the negative 20. Why impossible? You look at the nice oil drop on the top right. It could be charged because of, let's say, electrons. So you have electron, 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 electron. It becomes negatively charged. Each of these electrons has a charge of negative E. E is a constant 1.6 times 10 negative 19 coulomb. So if your charge is made of electrons and protons, which both have this value constant of 1.6, you cannot go smaller than that lah. So 8.0 times 10 negative 20 is way too small to be possible. No, we cannot have that. Okay, if you have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, then you are 8e, negative or positive, then yes, that is allowed. You must be a whole number multiple of e. This is too small. So you want to say that the minimum charge is supposed to be e. 1.6 times 10 to negative 19. That's the reason why this e is called elementary charge. All charge in the world is combination of many e's, many electrons together. Okay, so if you say the charge is too small, doesn't really hit on the point of this charge is quantized. Oh, we can talk about quantized. So other possible solutions, maybe you can say it's a not integer multiple of E. Multiple, what else can I accept? Smallest integer is 1. 1E. Or you can say charge is quantized. And this is not going to give you an integer. Remember, you must explain. So don't just say minimum charge. Or charge too small. Minimum charge is this thing, but it's too big. So check your work and see, do you talk about minimum charge or not integer multiple or something like that? Okay, if there's no other solutions or suggestions, then we look at the next part B. Oil drop in vacuum between two plates. Oh, oil drop. Remember when I mentioned if there's oil drop, especially if they give the mass, chances are there's going to be a gravitational force. You cannot say the gravitational force is negligible. So they give us all the values: uniform E, field strength, E, distance of plate, D, electric field, already given to us, okay. Oh, the D is here, sorry, D already got. The oil drop moves vertically downwards with constant speed. Whoa, what does that mean? Constant speed means no acceleration. There is no change in velocity. which tells me that there is no net force. I'm going to write down these facts first. Later, it might be useful. The very first step is calculate the potential difference between the plates. I need something that has V in it, an equation. Oh, but I know E and D, so maybe I'll start off with the first uniform field equation, V over D. So field strength will be 2.1 times 10 to the 5. It's given right here. Then we have V, which we need to find potential difference. We don't know. Distance is 8 millimeters on this side. So we're going to have 8.0 times 10 negative 3. End of the day, we press calculator correctly. We should get a voltage of 1680, I think. Calculate that day. 1680 volts. If I round it off to 2SF and I put it in standard form, then this can be written as also 1.7 times 10 to the 3. Different ways of writing it lah. So it's also okay, it's also okay. If A, any answers 2, 3 SF is okay. Standard form is preferred. This thing times 10 to the 3 is a standard form where you put in prefix. Oh, one mark here is if you got write E equals to V over D somewhere in your working. So you look and see your working, do you have E equals V over D? If got, give yourself one check mark for the equation. If you didn't write this out, but you got show in the working, can lah. If I can recognize that this is E and this is D, I can give. But it's a bit risky. So recommend whenever you're writing working, start off with the equation you're going to use, then only plug in the values. So it's very clear you state, I am using this equation. Give me the bonus. Last part is gonna explain something. So we said there's an oil drop moving at constant speed and it's going downwards and there's forces on it. Explain. Explain is a key word. Why? How the motion of oil drop show is in equilibrium. So the motion that they give to us is constant speed. Equilibrium is a concept where you say there is no net force and no net torque or moment on the object. Of course, in this case, moment is a bit weird. The moment is usually for rotating rods or something like that. But this is just force, so we're going to look at no net force. So we're going to tie these ideas together. No net force and constant speed or constant velocity. So we can say that constant velocity, what does it mean? It means no acceleration, no change. You're always 5 kilometers per hour, there's no change. So constant velocity means no acceleration. What does no acceleration mean in terms of force? So no resultant force. And that is the definition of equilibrium. This object, this oil drop, although it is moving, V, it is in equilibrium because it's not moving faster, it's not moving slower. So if you look in your solution, okay, how do you find where to mark? The first one is to look out for constant velocity means no resultant force. So you make a link, constant velocity, no resultant force. Then that's one mark. If you didn't mention acceleration, that's okay. They assume you know the link from velocity to resultant. Okay, so check out if you got mentioned no resultant force. That's a key one. Definition of equilibrium. If you wrote constant speed instead of velocity, I think can. In this case, since they say constant speed, yeah, can accept. So all those that you write speed here, can, speed. Where else did we say speed? No else. Right. Okay, no other. Oh, resultant force, another word is net force. So some of you prefer to use the word net force. It means the same thing. Net or resultant. Okay, let's go on to the second page. No movement nah. Wait. It's moving though. Constant speed. So it is moving, but at a constant speed. So cannot say no movement. Sad face. I will give you a sad face. No movement means no displacement. Yeah, moving. Remember, we are moving. but steady. No faster, no slower. Okay, any questions? Any other questions for this first page so far? The charge or the equilibrium? If not, let's go on to the right side where we have to do some calculation now. Okay. Determine the charge of the oil drop. Wow, where do we even start, man? Okay, charge. Okay, we slow down, we think of charge. Q. We need an equation that has Q in it. And so far, as long as I can remember, there's only one. F equals to QE. This is the force, the electric force. So somehow I need to figure out a way to use this equation. And if there's force involved, especially in electric field, chances are you will need to use Newton's second law. So maybe we will start with that. Newton's second law says net force is mass times acceleration. But hold up. Just now we just talked about this object. This oil drop is heavy, right? So there will definitely be a gravitational force trying to pull it down. This is Fg, which is mg. But there's also some force that's keeping it up. That is our electric force. I mean, it has to be pointing up, it cannot be pointing down, right? Two forces pointing down doesn't make sense. You want to keep it in equilibrium. So if you want these two forces to cancel out, they should be pointing in opposite direction. And is it speeding up? No, it's at constant velocity, which means you are not accelerating. Zero. There is no net force. Zero. So I can sub this out and say, oh, so no net force. So no net force means this force cancel out with this force. I can call them one negative, one positive, or I can just say QE equals to mg. Equal magnitude, opposite direction, they are in equilibrium, although this object is moving with a certain speed v. Here is where I can find my Q. So then Q equals to mg over E. Let's sub in the values. Okay, Q is, what is the M? You can go and find the M. Hang on a second. Mass. Okay, mass is down here. 6.8 times 10 to the negative 15. G is 9.81 and electric field strength is given to us down here. So I'm going to write that 2.1 times 10 to the 5. Okay. This is a 3-mark question now. Actually, the first one, if you already got equate QE equals to mg, the upwards force equals the downwards force, they cancel out each other, then this is 1 mark. Or if you kind of wrote on your paper and draw a diagram or something like that, QE is pointing up, mg pointing down, that can also be your C1 mark for this one. Then if we find the value here, 3.1766 times 10 to the negative 19, and we write our answer, and say I write 2 SF, 3.2, 10 to the negative 19. That is 1 more mark. I accept if it is 3.18. Also okay. That is the 3 SF, this is the 2 SF. Now the final one. What is the sign of this charge? We have to go back to the diagram to determine what the sign is. So we know that in order to counter weight, you must have some kind of force pointing upwards. If not, you cannot. So this force point up. And there's a weight point down. Now we look at the setup of the electric field. This one is positive. This one is, what is this? This is ground, a symbol for earth, ground or earth, which means here will be 0 volts. Low potential. So electric field lines will point from high potential to low potential, so something like this. Yeah, I draw a few. There's one more here, but I didn't draw all. Okay, so this one, what kind of particle will go against the electric field lines? There's only one rebel, and we know it. It's a negative charge. So negative charge, if the electric field point down, the force of electric Electric force will point up. Negative charge. So right here, negative. Hence, you need to write here negative. So if you wrote positive, unfortunately, it's not correct. So this is negative charge. One more point here. So 1, 2, 3. Okay, let's go on to part C. Part C now. You have your setup, it's nice and steady. But now, the magnitude of potential difference between the plate is decreased. If you have your equation E equals to V over D, say this is delta V, okay? This one is decreased. Then, how? What happened to the, why the oil drop accelerate downwards? Let's think through the flow of thoughts here. When the potential difference decrease, your electric field strength decrease, which also means your electric force, F equals to QE. Since E decrease, force also decrease. Everything decrease, all the electric decrease. So maybe let's start with that train of thought first, because we need to explain now. So when the potential difference decrease, electric field strength, E field strength, and force, electric force, must say electric force because got too many force, decreases. Space to write already. Rub off this decreases. This is pulling the link between this equation and F equals to QE. Now we look back at the diagram on the top left. At first they are balanced, but now if this one becomes smaller, then somebody is going to win. The mg is still the same old super large value, or no, didn't decrease at all. But now your electric F, your QE becomes so small. So now you're off balance already. So there's going to be a net force pointing downwards. And that will cause, net force going to cause an acceleration downwards. So that's our second sentence. So weight is now larger than the electric force. And you can talk about the resultant force that is downwards. Resultant force is downwards, causing acceleration downwards. How do we hunt for ideas here? First idea I'm looking for is, did you know how the electric force will change if I change the potential difference? Electric force decreases. Must mention electric force. Don't just say force decrease. Which force? So many force here. Electric force. This one is B1. So hunt in your working, you talk about electric force. The second point is talking about how weight become larger than electric force, leading to resultant force downwards. So this is what I'm looking for in your explanation somewhere. You talk about changes to the force and the net force. Go on to the next part. Describe the change to the pattern of the field lines representing the uniform field as the potential difference increase. Decrease. So just now we say E equals to V over D, right? If your potential difference decrease, your electric field strength decrease. How will we see that in the pattern of the field lines? Remember we draw, if the lines are very far apart, very weak field, weak. If the lines are very strong, strong, they are close together. This is a strong field. So your field is getting weaker and weaker, means their separation should become bigger. They become further apart because become weaker already ma. So you want to explain and say that the field line separation increase. Or you can say the field lines are further apart, more spacing. Also can, same idea, looking for your concept here. So check your work. If you got this idea that the lines become far apart, when they become weaker, then That's accepted. Less dense. Can lah. I understand what you're trying to say. The density within an area, lines per area, can? Okay, less number of lines. Less number of lines is a bit sketchy. I will put a warning sign there if you wrote less number of lines. But for now, can accept lah. Less number of lines in a space or a region. Then that's correct. Less number of lines between the plates, can. But that one is, explain more detail. Less number of lines. Where I draw far apart. Still the same number of lines. More spread out. More spread out. More spread out. I just said it. Then very good. You post there. Yes, more spread out is allowed. More spread. Further apart. Less lines. Less number. Or less lines between plates. This one can add on here. Less lines between plates to clarify. Good suggestions. Good suggestions. Go to the last part then. So you have two force, new force, X and Y, that can act on oil drop when it's in air, but cannot act when it's in a vacuum. Oh, that tells me a hint. Cannot act when it's in vacuum. So these two forces that we're going to guess now, they must have a medium. Must have a medium. Like air. It must be in air, must be in water, but cannot be in vacuum. Force X act on oil drop when it is stationary or moving. So X, you will see this force when the particle is stationary or moving. Both. Force Y can only act when it is moving. So only when you move, you see this force appear. Wow. What force is this? It's been a while since we saw these forces. The second one, I can very quickly tell you, there's only one force I know that only appears when you move. This force is proportional to velocity or velocity squared, also known as air resistance or drag force. So all the possible suggestions here is air resistance. You can say drag force. You can say viscous force. All this applies to an object when it is moving in a fluid. So I should add here, must have a fluid medium. Air is a fluid, by the way. We think of fluid as water or liquid, but air is also a fluid. It flows around us, it bends, it swirls, it's a fluid. Okay, that's the first one. A second one. The first one, First one, whether you move or you not move also is there. This one is what we call the upthrust force. We have not seen this force in a very long time. So imagine we are in a fluid. The air is a fluid. Air is a fluid. If you are in a vacuum, you only have mg and electric force, for example. But if you are in air or any fluid, water, air, oil, honey, then you will also have upthrust, always opposite to mg. And you have one more, which depends on where you're moving. Let's say I'm moving down. Okay, sure. Then, cannot be moving down already. Okay, too many force already. Let's say I'm moving up. Then I will have this resistive force pointing down. This is drag. So actually, in real life, there's actually 4 forces acting on objects moving in fluids. So these two you can check out. This is B1, this is B1. Can we accept resistive force and friction? Those are what I call gray area, because friction can be static friction or friction on the table, friction on the floor. Air friction, air resistance. So I can accept, but you put a warning sign there and say friction is not specific enough. There are many types of resistive forces and friction. A resistive force, which type of resistive force? Static friction, contact friction, air friction. So this one I can accept for now, but put a warning sign. Best is you want to specify the details. Drag, viscous. For fluids. What is D1 mg? Oh, D1 mg. Cannot ah. These are the forces that must have medium. In vacuum, they cannot exist. Alright, a reminder here. These forces cannot exist in vacuum. If you say mg, what gravitational force ah? Gravitational force can act in vacuum. No problem. So it cannot be any of these. These two are only not in vacuum, only they will appear. So cannot say gravity. No, cannot.